Students, this video is the continuation of the discussion of properties of eigenvalues. Let's look at the property. If an nth order square matrix A has eigenvalues lambda 1, lambda 2, etc. lambda n, then the matrix A raised to m, which is the mth integral power of A, obtained by multiplying A to itself m times, will have eigenvalues of the format lambda 1 raised to n, lambda 2 raised to m, lambda n raised to m, etc. Which says that if you know the eigenvalues of matrix A, then the eigenvalues of A raised to m is obtained by just raising the eigenvalues of A to the mth power. Let's look at the proof. Assume that lambda is the eigenvalue of matrix A and the characteristic equation A minus lambda into x equal to 0 gives us the relation x equal to lambda x, where x is the eigenvector. If we pre-multiply both sides of this relation by matrix A, by associativity of matrix multiplication, you get this as A square x, and lambda being taken outside the matrix multiplication being a scalar, you get the expression as lambda into Ax. When Ax is replaced by lambda x, you get the expression A square x is equal to lambda into lambda x, which can be written as lambda square x. When you pre-multiply this equation again by A on both sides, you get the result A cube x equal to lambda cube x. Continuing the process of pre-multiplication with matrix A, you get the general result A raised to mx equal to lambda raised to m into x, from which you can write A raised to mx minus lambda raised to m I into x equal to 0, and this can be written very much similar to the format of the characteristic equation. When we write A minus lambda I into x equal to 0, we say that lambda is the eigenvalue of A. Hence, looking at this expression, we can say that lambda raised to m is the eigenvalue of A raised to m. Hence, you can conclude the proof. Next property says that if A is a non-singular matrix with lambda as the eigenvalue, then the matrix adjoint A will have the eigenvalue determinant of A divided by lambda. Let's look at the proof. Assume that lambda is the eigenvalue of A, and we get the relation Ax equal to lambda x by the characteristic equation of A. If you pre-multiply this equation by matrix adjoint A on both sides, you get the relation joint A into x equal to lambda times adjoint A into x, because lambda is taken outside the matrix multiplication being a scalar, and here we apply the associativity property of matrix multiplication. From class 12, we know the well-known result joint A into A equal to determinant of A into I, from which we evaluated the formula A inverse equal to adjoint A divided by determinant A. When you substitute this property here, you get determinant A into x equal to lambda times adjoint A into x, which can be written as determinant A divided by lambda into x equal to adjoint A into x. When you bring both the terms to one side and take x as the common outside, you get an expression which is much similar to the standard characteristic equation. So you can say that determinant A by lambda will be the eigenvalue of matrix adjoint A, because this is very much similar to the characteristic equation A minus lambda I into x equal to 0. Hence, you can prove this property. Cayley-Hamilton theorem says that every square matrix satisfies its characteristic equation. In simple terms, it would mean that if you consider an nth order square matrix with characteristic equation given by determinant of A minus lambda I, which takes the general format, which is the expression involving powers of lambda and equated to 0. This is the expression known to as Cayley-Hamilton theorem says that if you replace lambda by matrix A, the result is true. That is, this particular equation is also satisfied by the matrix A. Quick notes on Cayley-Hamilton theorem. If you multiply both sides of the characteristic equation by A raised to a minus n, you obtain an equation in terms of powers of A raised to m, A raised to a minus 1, A raised to a minus 2, etc. From where you can write the expression A raised to m in terms of lower powers of A. So, A raised to m can always be written as a linear combination of terms of powers of A of lower degree than m. If you multiply the characteristic equation involving A, both sides by A inverse, then you get the expression involving powers of A raised to n minus 1, A raised to n minus 2, etc. From which you can get the expression of A inverse in terms of n minus 1 powers of A. So Cayley-Hamilton theorem helps us to find the inverse of a matrix as well. Let's look at an example to understand the very essence of Cayley-Hamilton theorem. Here in this question, we are asked to verify Cayley-Hamilton theorem for a square matrix of order 2, and we are asked to find the inverse using Cayley-Hamilton theorem. Also, we are asked to check if we could express a fifth degree polynomial in A as a linear polynomial in A with the help of Cayley-Hamilton theorem. Let's look at the solution. To prove Cayley-Hamilton theorem, we have to depend on characteristic equation of A. We found the characteristic equation using the formula determinant of A minus lambda I equal to 0. Having found the characteristic equation, we have to check whether this particular equation is satisfied by the matrix A. For that, we replace lambda by matrix A. So we have to evaluate A square minus 4A minus 5A. We evaluate A square 4 times, A is considered, and 5 times identity matrix is evaluated. When you evaluate the LHS, you are getting the 0 matrix as the solution. Hence, Cayley-Hamilton theorem is verified. Now, we have to find A inverse. To find out A inverse, we multiply the characteristic equation in terms of A, both sides, by A inverse. And the reduced form is A minus 4I minus 5A inverse. A square when multiplied by A inverse becomes A multiplied by A inverse becomes identity matrix, I multiplied by A inverse becomes A inverse. From this expression, you are finding the expression for A inverse, which is 1 by 5 times A minus 4I. You substitute for the matrix A and 2 by 2 identity matrix here to obtain the answer for A inverse. So, Cayley-Hamilton theorem allows us to find out A inverse without using the formula A inverse is equal to joint A divided by determinant A. Now, we are going to check if the fifth degree polynomial in terms of A can be reduced to a linear polynomial of A. For that purpose, we divide the fifth degree polynomial by the characteristic equation. Instead of A, we just make use of lambda. When you try to divide the fifth degree polynomial by the characteristic equation of A, you get a cubic polynomial as the quotient and remainder as a linear polynomial. With the remainder theorem saying dividend is equal to divisor into quotient plus remainder, you could write the fifth degree polynomial equal to the characteristic equation or the characteristic polynomial into cubic polynomial, which is the quotient plus remainder. We know that this is the characteristic equation itself and it always assumes the value 0. Hence, this particular product disappears and the answer for the fifth degree polynomial will be lambda plus 5. So, after replacing lambda by A, you get the expression that fifth degree polynomial in A using Cayley-Hamilton theory can be written as a linear polynomial in A. Let's look at another example to evaluate A raised to 8 if we are given A as a 2 by 2 square matrix. We evaluate the characteristic equation of A and we obtain a polynomial in terms of lambda. We know that by Cayley-Hamilton theorem, lambda can be replaced by matrix A. So the equation reduces to A square equal to 5 times I. Since you have to evaluate A raised to 8, you raise both sides with the power 4 so that you get the answer as A raised to 8 is equal to 625I. In the next problem, you're asked to find out A inverse for a 3 by 3 square matrix along with verification of Cayley-Hamilton theorem. So first we evaluate the characteristic equation of A, which is given by determinant of A minus lambda I equal to 0, and being a 3 by 3 matrix considered, you get a cubic polynomial in terms of lambda. To verify Cayley-Hamilton theorem, what we do is we replace lambda by matrix A. So we have to evaluate A cube, A square and multiply by all these scalar values. We evaluate A square by matrix multiplication and A cube is found using A square into A, and we check for the characteristic equation whether it is reducing to a 0 matrix. We evaluate the answer as 0. To find out A inverse, what we do is we multiply both sides of the characteristic equation involving A with A inverse. After multiplication, we see that we get an expression with the degree 2, and from this equation you find out the expression for A inverse. To find out A inverse, you have to find A square A. A square is already calculated. So using the answer for A square, and we evaluate this equation to find out the answer for A inverse. So without using the formula, A inverse equal to determinant. Without using formula of A inverse, which is equal to adjoint A divided by determinant A, we could find out the A inverse using Cayley-Hamilton theorem. Thank you all.